Welcome to this coding walkthrough. In this session, we're tackling the problem number 2136, earliest possible day of full bloom. We'll explore the challenge, discuss different approaches, and break down the solution step by step. Let's dive in. In this problem, you are tasked with determining the earliest possible day when all seeds in a garden will fully bloom. You are given two integer arrays, plant time and grow time, both of size n. The value at index I in plant time represents the number of full days it takes to plant the ith seed. Similarly, the value at index I in grow time represents the number of full days it takes for the ith seed to grow and become a fully bloomed plant once planting is complete. Seeds can be planted in any order, but it's important to note that you can only plant one seed at a time. This means you must finish planting one seed completely before moving on to the next. Furthermore, after finishing the planting of a seed, it will take the specified number of grow time days for that seed to bloom. Your goal is to return the earliest day on which all seeds will be blooming, considering the constraints of planting order and the rules for growth time. The output for this problem is a single integer that represents the earliest possible day when all seeds are blooming. To better understand the problem, let's explore some examples. In the first example, the arrays are plant time equals 1, 4, 3, and grow time equals 2, 3, 1. The output here is 9. To achieve this result, we need to determine the optimal order to plant the seeds. Specifically, we need to consider both the time it takes to plant each seed and the time it takes for each seed to grow after planting, ensuring that the latest bloom day across all seeds is minimized. For the first example, the optimal planting order is as follows. First, plant seed 2, which has a plant time of 4 days and a grow time of 3 days. Planting begins on day 1 and finishes on day 4. The seed will then bloom 3 days later, on day 7. Next, plant seed 0, which has a plant time of 1 day and a grow time of 2 days. Planting begins on day 5 and finishes on day 5. This seed will bloom 2 days later, also on day 7. Finally, plant seed 3, which has a plant time of 3 days and a grow time of 1 day. Planting starts on day 6 and finishes on day 8, with the seed blooming the next day, on day 9. The latest bloom day across all seeds is day 9, which is the final output for this example. Now, consider the second example with plant time equals 2, 3, 1, and grow time equals 5, 1, 4. The output here is 8. The optimal planting order is as follows. First, plant seed 0, which requires 2 days to plant and has a grow time of 5 days. Planting begins on day 1 and finishes on day 2, and the seed blooms 5 days later, on day 7. Next, plant seed 2, which requires 1 day to plant and has a grow time of 4 days. Planting begins on day 3 and finishes on day 3, and the seed blooms 4 days later, also on day 7. Finally, plant seed 1, which requires 3 days to plant and has a grow time of 1 day. Planting begins on day 4 and finishes on day 6, with the seed blooming the next day, on day 7. The latest bloom day across all seeds is day 8, which is the output for this example. In the third example, the arrays are plant time equals 1 and grow time equals 1. Here, there is only one seed to plant. The planting of this seed starts and finishes on day 1, and it blooms 1 day later, on day 2. Since there is only one seed, its bloom day is the latest bloom day, and the output is simply 2. This example highlights the simplicity of the problem when there is only one seed to consider. Lastly, let's discuss some key edge cases that you should keep in mind. First, if there is only one seed, the result is simply the sum of its plant time and grow time, as there are no other seeds to consider. Second, when all seeds have the same grow time, the order of planting is determined solely by their respective plant time values. Seeds with longer planting times should be planted earlier to avoid delaying their bloom. Finally, for large input sizes, where n is as large as 100,000 and plant time and grow time values are at their maximum, it's critical to ensure that the algorithm is efficient and can handle these constraints within a reasonable time frame. By carefully considering these scenarios, you can build an effective solution to the problem. To tackle the problem of finding the earliest possible day of full bloom, we first consider a brute force approach. The intuition here is to explore all possible planting sequences for the seeds and simulate the growth process for each sequence. Specifically, this would involve generating every permutation of the seeds, simulating planting and growing them in that order, and then calculating how many total days are required for all seeds to bloom. While this method guarantees the correct result, its computational complexity is a major drawback. Generating permutations for n seeds takes factorial time, O(n), and simulating each sequence adds an additional O(n) factor, leading to a total complexity of O(n). (n). For small values of n, this might be feasible, but as n grows, the time required quickly becomes impractical. For instance, even with just 11 seeds, the number of permutations exceeds 39 million. Recognizing this limitation, we turn to an optimized greedy approach that leverages key insights about the problem structure. The optimized greedy approach is based on the observation that the order in which seeds are planted plays a crucial role in minimizing the total bloom time. Specifically, seeds with longer grow times should be prioritized because their growth can overlap with the planting of subsequent seeds. This overlapping effect reduces idle time and ensures an efficient use of days. To implement this strategy, we pair each seed's planting time and grow time as a tuple, then sort these tuples in descending order of grow time. If two seeds have the same grow time, their order doesn't matter. Once sorted, we simulate the planting process using a simple loop. For each seed, we track the cumulative planting time, referred to as current day, and calculate the bloom time as the sum of this planting time and the seed's grow time. The maximum bloom time across all seeds is the result. This approach is much more efficient, with a complexity of O(n) log n for sorting and O(n) for the planting simulation. While the greedy nature of this solution may initially seem non-intuitive, it's both effective and easy to implement, making it a strong candidate for the final strategy. The final approach, based on the greedy strategy, effectively minimizes the total bloom time by focusing on the overlap between planting and growing periods. By prioritizing seeds with longer grow times, we ensure that the most time-consuming growth processes begin as early as possible. This method achieves an optimal time complexity of O(n) log n, which is efficient given the need to sort the seeds. Of course, no solution is without trade-offs. The greedy approach assumes that sorting seeds by grow time is the optimal strategy, an insight that requires a clear understanding of the problem structure. However, this assumption holds true, as validated by edge cases and problem constraints. When compared to alternatives, such as the brute force method or potential dynamic programming solutions, the greedy strategy stands out for its simplicity and efficiency. The key insight here is recognizing the importance of planting order and how it can minimize idle growth time. This realization serves as that aha moment that unlocks the problem's solution. The final algorithm, shown here, is both concise and elegant, iterating through the sorted seeds and tracking the cumulative planting time to compute the maximum bloom time efficiently. To solve this problem, we need to determine the optimal order to plant a set of seeds such that the total time for all seeds to bloom is minimized. Each seed has two attributes. The planting time, denoted as P_i, is the time it takes to plant that seed, and the growth time, denoted as G_i, is the time it takes for the seed to fully bloom after it has been planted. Now, the key challenge lies in deciding the order in which we plant these seeds, as the planting times accumulate sequentially, while the growth times determine how long each seed takes to bloom after planting. To represent the input, we can store the seeds as a list of tuples, where each tuple contains the planting time and growth time of a seed. For example, 3, 4, 2, 5, 1, 6 represents 3 seeds with their respective planting and growth times. A critical observation is that the total bloom time for all seeds depends on both the planting times and the growth times, meaning the order of planting directly impacts the result. So, our task is to find the most efficient planting sequence to ensure that the last seed blooms as early as possible. To achieve this, we make an important observation: planting seeds with higher growth times earlier allows them to start growing sooner, which minimizes the overall bloom time. This leads us to the next step: sorting the seeds. We sort the list of seeds in descending order based on their growth times, G_i. If 2 seeds have the same growth time, their order doesn't affect the result. By doing this, we ensure that seeds with the longest growth times are prioritized to start growing earlier, which is optimal since their growth duration has the most significant impact on the total bloom time. Once sorted, we simulate the planting process. We initialize 2 variables, current_time, which tracks the cumulative planting time as we move through the seeds, and max_bloom_time, which keeps track of the latest bloom time among all seeds. For each seed in the sorted list, we first add its planting time to current_time. Then, we calculate the bloom time for that seed as the sum of current_time and its growth time. Finally, we update max_bloom_time to ensure it always holds the maximum bloom time encountered so far. Once all seeds are processed, max_bloom_time will give us the minimum total bloom time for all seeds to bloom. The key idea behind this algorithm is a greedy approach. By always planting seeds with the highest growth times first, we ensure that the most time-consuming seeds start growing as early as possible, minimizing delays. Sorting the seeds by their growth time in descending order is essential to achieve this, as it allows us to efficiently manage the planting sequence. Let's analyze the complexity. Sorting the seeds takes O and log n time, where n is the number of seeds. Simulating the planting process involves iterating through the list once, which takes O n time. Therefore, the overall time complexity of the algorithm is O n log n, dominated by the sorting step. As for space complexity, the algorithm is efficient, requiring only O1 additional space beyond the input list. This makes it well suited for large inputs. We also need to consider edge cases. For example, if there's only one seed, the total bloom time is simply the sum of its planting and growth times. If all seeds have identical growth times, the order of planting doesn't matter, as sorting will not affect the output. Lastly, if all growth times are 0, the result is just the sum of all planting times, since the seeds bloom instantly after planting. To implement the algorithm, we use a list of tuples to represent the seeds and their attributes, where each tuple contains the planting and growth times of a seed. The sorting operation is performed directly on this list. We also use two variables, current_time to track the cumulative planting time and max_bloom_time to keep track of the latest bloom time encountered during the planting process. Here's the pseudocode for the solution. First, we sort the seeds by their growth times in descending order using a lambda function. Next, we initialize current_time and max_bloom_time to 0. Then, we iterate through the sorted list of seeds. For each seed, we add its planting time to current_time and calculate the bloom time by adding the growth time to current_time. We update max_bloom_time to the maximum of its current value and the bloom time of the current seed. Finally, after processing all seeds, we return max_bloom_time as the result. This simple and efficient approach ensures that we compute the minimum total bloom time for all seeds. Let's walk through an example to see how the algorithm works. Suppose the input is a list of seeds with their planting and growth times, 1, 4, 2, 3, 3, 2. First, we sort the seeds by their growth times in descending order. In this case, the list is already sorted as 1, 4, 2, 3, 3, 2. Next, we simulate the planting process. We initialize current_time to 0 and max_bloom_time to 0. We start with the first seed, 1, 4. After planting it, current_time becomes 1, and the bloom time for the seed is current_time plus its growth time, which is 1 plus 4 is equal to 5. We update max_bloom_time to 5. Moving to the second seed, 2, 3, we add its planting time to current_time, making current_time 3. The bloom time for the seed is now 3 plus 3 is equal to 6, so we update max_bloom_time to 6. Finally, we proceed to the last seed. For the third seed, 3, 2, we add its planting time to current_time, which becomes 6. The bloom time for the seed is calculated as current_time plus its growth time, which is 6 plus 2 is equal to 8. We update max_bloom_time to 8. At this point, we have processed all the seeds, and the final value of max_bloom_time is 8. This means the minimum total time required for all seeds to bloom is 8. This example highlights how the sorting step and the greedy planting process work together to ensure an optimal solution. By always prioritizing seeds with longer growth times, we achieve the earliest possible day of full bloom for all seeds. This implementation solves the problem by prioritizing seeds with longer growth times to minimize the time when the last seed blooms. First, we combine the planting and growth times into a list of tuples for easier manipulation. Then, we sort these tuples based on growth times in descending order. The rationale behind this sorting is that seeds with longer growth times should be planted earlier to avoid delaying their full bloom. Next, we initialize two variables, current_plant_time to track the cumulative planting time as we process each seed, and max_time to record the latest point when all seeds are in full bloom. For each seed, we add its planting time to current_plant_time, which accumulates the time spent planting seeds sequentially. We then calculate the full bloom time for the current seed as current_plant_time plus grow. If this value is larger than max_time, we update max_time. Finally, once all seeds are processed, the value of max_time represents the earliest possible day when all seeds are in full bloom. This approach ensures an optimal solution with a time complexity of O(n log n) due to sorting and linear processing of the seeds. This is the Java implementation of LeetCode problem number 2136, earliest possible day of full bloom. The logic mirrors the Python solution, where we sort the seeds by descending grow time and calculate the full bloom day iteratively. Key differences include explicit type declarations, usage of Java's arrays.sort for custom sorting, and handling arrays instead of tuples. The implementation is efficient and processes the input in O(n*log n) due to sorting. To solve this problem, we start with an example where the planting times are 1, 2, 3, and the growing times are 3, 2, 1. The first step is to combine these two arrays into a list of tuples, where each tuple represents the planting and growing time for a particular seed. This gives us 1, 3, 2, 2, 3, 1. Next, we sort this list in descending order based on the growing times. The sorting ensures that seeds with the longest growing times are planted first, as this minimizes the overall time for all flowers to bloom. After sorting, the list remains 1, 3, 2, 2, 3, 1, since it's already in descending order of growing times. Now, we initialize two variables, current_plant_time to keep track of the cumulative time spent planting seeds, and max_time to store the earliest possible day of full bloom. Both start at 0. We then process each seed in the sorted list. For the first seed, 1, 3, we add the planting time, updating current_plant_time to 1. The full bloom time for this seed is the planting time plus the growing time, so max_time becomes 4. For the second seed, 2, 2, the cumulative planting time increases to 3, and the bloom time for this seed leads to max_time being updated to 5. Finally, for the last seed, 3, 1, the cumulative planting time reaches 6, and the bloom time results in a max_time of 7. The earliest day when all flowers are in full bloom is therefore 7. Let's look at another example where the planting times are 2, 3, 1, and the growing times are 5, 4, 2. First, we combine these into tuples, resulting in 2, 5, 3, 4, 1, 2. Then, we sort this list in descending order of growing times, so that seeds with longer growing times are prioritized for planting. After sorting, the list remains 2, 5, 3, 4, 1, 2. As before, we initialize current_plant_time and max_time to 0, and will process each seed in this sorted order. Starting with the first seed, 2, 5, we add the planting time to get current_plant_time of 2. The bloom time for this seed is 7, so max_time is updated to 7. For the second seed, 3, 4, the cumulative planting time increases to 5, and the bloom time updates max_time to 9. Lastly, for the seed, 1, 2, the planting time reaches 6, but the bloom time of 8 does not exceed the current max_time of 9. Thus, the earliest full bloom time for this example is 9. Now, consider a simpler case where all planting times and growing times are equal, with plant time equals 1, 1, 1, and grow time equals 1, 1, 1. Here, the combined list of tuples is 1, 1, 1, 1, 1, 1. Since all growing times are identical, sorting the list in descending order of growing times doesn't change its order, so it remains 1, 1, 1, 1, 1, 1. Again, we initialize the current_plant_time and max_time variables to 0 and begin processing the seeds. For the first seed, 1, 1, we add the planting time to get current_plant_time of 1, and the bloom time updates max_time to 2. For the second seed, 1, 1, the cumulative planting time becomes 2, and the bloom time updates max_time to 3. Finally, for the last seed, 1, 1, the planting time increases to 3, and the bloom time updates max_time to 4. Since all seeds had identical planting and growing times, the overall earliest day of full bloom is 4. This demonstrates how the algorithm efficiently calculates the result by prioritizing seeds with higher growing times while keeping track of cumulative planting time to ensure all flowers bloom as early as possible. To analyze the time complexity of this solution, we start by breaking it into its key steps. First, we combine the plant time and grow time lists into tuples using the zip function. This operation requires iterating through both input lists, each of length n, resulting in a time complexity of O, n. Next, these tuples are sorted based on their grow time values in descending order. Sorting a list of n elements in Python uses timsort, which has a time complexity of O, n log n. Finally, we iterate through the sorted list to compute the earliest full bloom time. This loop runs exactly once for each tuple, and each iteration involves constant time operations like updating variables. Therefore, this step is O, n. Combining these, the overall time complexity of the algorithm is determined by the dominant step, which we will explore further. Adding up the complexities of the steps, we get O, n, for creating the tuples, O, n log n, for sorting, and O, n, for the loop. This simplifies to O, n log n, as the sorting step dominates the overall complexity. Now, considering the space complexity, the input lists plant time and grow time each require O, n, space. The zip operation creates an additional list of tuples, also requiring O, n, space. Sorting is done in place using Python's timsort, which requires only O, 1, auxiliary space. Finally, the integer variables used in the implementation like current_plant_time and max_time contribute O, 1, to the space complexity. When combined, the total space complexity is driven by the input size, which we will now summarize. Combining the space requirements, we see that O, n, for input storage, O, n, for tuple storage, and O, 1, for sorting and variables add up to O, n. This linear space complexity is efficient and scalable for large inputs. To put this into perspective, a naive approach to solving the problem could involve generating all possible permutations of the planting order to determine the minimum full bloom time. Since generating permutations of n elements has a time complexity of O, n, this would be computationally infeasible for large values of n, such as when n exceeds 10. In contrast, the current greedy approach, which sorts seeds by descending grow time, ensures an optimal solution with a far more efficient O, n log n, time complexity. This is achieved by prioritizing seeds with longer growth times to minimize their waiting periods. When we analyze the best, average, and worst-case scenarios for this algorithm, the time complexity remains O, n log n, across all cases. This is because sorting, the most computationally expensive operation, is required regardless of the order of the input. Even if the seeds are already sorted in the optimal order, sorting still takes O, n log n. The mathematical proof of the algorithm's complexity confirms this. Sorting contributes O, n log n, while the additional operations, such as zipping and looping, add O, n. Since O, n log n, dominates, the total complexity is O, n log n. In conclusion, this solution is both time-efficient and space-efficient. The greedy strategy ensures optimal results in O, n log n, time, a significant improvement over the naive O, n, approach, while maintaining a linear O, n, space complexity, making it well-suited for large-scale inputs. When tackling this problem, there are a few common mistakes to watch out for. First, not considering all permutations when using a brute force approach can lead to incorrect results. For instance, if the order in which seeds are planted affects the bloom time, failing to test all possible sequences might result in suboptimal solutions. Another frequent issue is ignoring edge cases. Minimal input sizes, such as a single seed or no seeds at all, often reveal flaws in your logic. Your solution must handle these cases gracefully without unnecessary computation. Misinterpreting the problem constraints is another pitfall. For example, overlooking the maximum input size, like n being less than or equal to 10 to the power of 4, can lead to inefficient solutions that time out. Always ensure your algorithm meets the upper bounds specified. Lastly, incorrectly calculating the total bloom time can be a major issue. If the bloom time depends on the order of planting, simply summing up growth times might not work. Make sure your solution accounts for any order dependency in the problem. Skipping optimization opportunities is another common mistake. If the problem allows for efficient techniques like sorting or dynamic programming, relying on brute force can mean missing the chance to significantly reduce time complexity. For example, sorting seeds by their growth time can sometimes simplify the calculations substantially. In interviews, it's also important to demonstrate strong problem-solving techniques. Recognizing patterns, such as whether the problem involves sequencing or permutations, is critical. Sorting or greedy methods are often helpful here, so identifying when order matters can give you an edge. It's also crucial to ask clarifying questions to ensure you fully understand the constraints and goals. For instance, does total bloom time refer to the latest bloom time among all seeds or the sum of their individual bloom times? Additionally, interviewers value discussions about trade-offs between time and space complexity. For example, while sorting has a time cost of O(n log n), it may simplify the solution significantly. Be sure to highlight edge cases, such as empty inputs or seeds with unusually large growth times, to show your thoroughness. Finally, if time allows, discussing alternative approaches even after implementing one can demonstrate a deeper understanding of the problem. This problem shares similarities with others you might encounter, making it useful to explore related challenges. For example, LeetCode 1834, the single-threaded CPU problem, involves scheduling tasks while adhering to constraints, which is conceptually similar to managing planting and bloom times. Another related problem is LeetCode 135, Candy, which uses a greedy algorithm to distribute resources based on specific rules. Additionally, LeetCode 452, minimum number of arrows to burst balloons, is an interval scheduling problem that requires optimizing the order of operations to minimize resources. Finally, LeetCode 1029, two-city scheduling, also emphasizes sorting and greedy approaches to achieve the best outcome. These problems share underlying patterns, such as sequencing, optimization, and order dependencies, making them excellent practice for honing the skills needed to solve the earliest possible day of full bloom. There are several alternative approaches to consider for this problem, each with its own trade-offs. A greedy approach, for instance, might involve sorting the seeds by their growth time or another metric to reduce complexity compared to brute force. This method has a time complexity of O(n log n) for sorting, followed by O(n) for processing. However, it may not always yield the optimal solution if dependencies between seeds exist. Dynamic programming is another option, especially when the problem has overlapping subproblems. While it can be effective, it often increases space complexity. Naive DP solutions typically have a complexity of O(n squared, but with optimizations, this can sometimes be reduced. Finally, backtracking with pruning is useful for permutation-based problems, as it avoids unnecessary exploration of the solution space. However, its worst-case complexity remains exponential, up to O(n), depending on how effectively pruning is implemented. Each of these methods offers distinct advantages and challenges, so the best choice depends on the specific requirements and constraints of the problem. Great job making it to the end. Today, we tackled the earliest possible day of full bloom problem, explored key strategies, and discussed the importance of sorting and greedy techniques in scheduling problems. Thanks for watching, and be sure to like, subscribe, and stay tuned for more coding challenges. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!